Hello, welcome to lecture 14 of the course. This is lecture number 4 of module 2. In the last class, we saw how to quantize a discrete transmission line. In this lecture, we will learn how to write the quantized Hamiltonian in the form of a simple harmonic oscillator Hamiltonian. Also, we will learn how to quantize a transmission line resonator. So let us begin. In the last class, we discussed the circuit model for the transmission line. There we considered a collection of LC oscillators as shown in this figure, and each set or each branch of LC oscillators are equivalent, and in fact we have translational symmetry in the transmission line. Whether we go towards this direction or in the other direction, we are going to encounter the same kind of branch here. And there are many nodes there. Say for example, in the nth node we took the charge to be qn, and in the n plus 1th node the charge is taken to be qn plus 1, and so on. The current that is flowing towards this node is denoted as nth node as in, and the current flowing towards the node n plus 1 is denoted as in plus 1. And based on this model, we got this charge conservation. That is, for example, here in the nth node, if you look at it, the rate of change of the charge, time rate of change of charge in the nth node is equal to the charge that is flowing into the node and the charge the current that is flowing into the node and the current flowing out of the node. So this is what the charge conservation gives us, equation number 1. And equation number 2 is basically the voltage law, and this qn minus 1 by c and minus qn by c, that is the voltage drop that is happening across these nodes here, between nth node and n minus 1th node, and this voltage drop is responsible for this current in, and this is what we got as our equation number 2. And then we went on to discuss the continuum model for this discrete transmission line. What we have done is that we divided the transmission line into a number of unit cell of cell size of length a, and then considering the current to be uniform across this or continuous across this transmission line. Say for example, if we want to know the current at a particular node, say n, so we have to find the current at x is equal to na, and then using differential calculus, as I discussed earlier, so we can write this equation for difference in current between the nodes. And similarly for this charge conservation equation in the continuum domain, we get this equation, and that's how we got even the wave equation for the current. We found that the current flows through the transmission line as a wave with some velocity v, and v is given to be square root of small l into small c, where small l is the inductance per unit length and small c is the capacitance per unit length. Okay, so this is what we discussed, and then we went on to discuss the quantization of the transmission line. For that, first we discuss quantization of LC circuit, which is the basic unit cell of the transmission line. The idea was that to get the Lagrangian of the system. That's how we quantize. Canonical quantization procedure is just like that. You take any classical system, you first get the Lagrangian of the system, then find out the conjugate momentum, then work out the Hamiltonian, then look for canonically conjugate variables. Once you find that, then you can write down the commutation relation for these variables, and that's how you quantize it. So we adopted that method for LC oscillator also. Here we have written down the Lagrangian for the LC oscillator, taking charge as the coordinate. If we take charge as the coordinate, then we get this as our Lagrangian, and the fact that this Lagrangian is actually the correct Lagrangian, we can get it, we can verify it by putting it in the Lagrange equation of motion. If we do that, then we get this equation of motion, and which is well known. So the Lagrangian that is chosen is correct, and from that we get once we get the Lagrangian, we can find out the momentum, and momentum turns out to be minus or negative of this magnetic flux. Magnetic flux phi is L into I, and then we can find out the Hamiltonian. What we have found that this magnetic flux is basically the momentum and charge is the coordinate. So the Hamiltonian is a function of charge and the magnetic flux. So we get the ultimately the Hamiltonian for the LC oscillator, and we find that both the charge and the magnetic flux are canonically conjugate variables because it satisfies the Hamilton's canonical equation of motion, and therefore we can now do the quantization procedure. We just have to replace the charge and the magnetic flux by the corresponding quantum mechanical operator, and this commutation relation we just have to write commutation is equal to I h cross, and the Hamiltonian accordingly would be written in the operator form. And we discuss another thing that this LC oscillator can be quantized even by taking this magnetic flux as the generalized coordinate and charge as the generalized momentum, because in Hamiltonian formalism both coordinate and momentum are given equal weightage, so it's not going to make any difference. But as we saw that taking magnetic flux has a advantage over that of charge when we discuss quantization of the transmission line. So taking this we saw that we can actually quantize the LC oscillator. Only thing, the Lagrangian would be here different, and this Lagrangian is basically this part of this half Li square is the magnetic energy, and this q square by c is called the electrical energy or the charging energy. Now if we actually try to quantize the transmission line taking charge as the coordinate, not the magnetic flux, then we run into some trouble that also we discussed. For example, if we take, because as you can see from this Lagrangian that to get the Lagrangian we have to know the current as well as the charge. So suppose we know charge, then we have to find current I, and we saw that if we do that even in a particular single node, we cannot find out the current because this particular energy term results in an infinite sum, and which we cannot find. And you have to remember that we have to find actually this current, this magnetic energy term at each and every node, and even at particular node we are running into problem if we take charge as the coordinate. So therefore we saw that we have to take magnetic flux as the coordinate, and if we take the magnetic flux as the coordinate, charge is very easy to find out because it would be simply the time derivative to the magnetic flux multiplied by the capacitance, then we'll get the charge. Now what about the current? Where current can also be found very easily. We found that the current would be simply given by the difference of the fluxes at the nodes, and thereby we'll be able to find out the magnetic actually the current at a particular node, and then we can write down the Lagrangian. Now when we took charge as our coordinate, then the Lagrangian was magnetic energy minus electrical energy, but now we are taking the reverse, so it is electrical energy minus magnetic energy, and we got this Lagrangian for the discretized model of the transmission line. And we saw that we can actually get the Lagrangian for the continuum model of the transmission line as well. So taking the usual procedure, I saw that when in the limit a tends to 0, that means when cell size is vanishing, then we get the continuum model. But actually for quantization purposes, as I said, that we are going to take the discretized model along with some boundary condition. That's what we are going to discuss today. And this taking this discrete model, it is very straightforward to do the quantization of the discrete model. We just have to find out the momentum, and obviously momentum turns out to be the charge here, and then we can write down the Hamiltonian, and Hamiltonian is simply this, and we know that this momentum and this P and actually this magnetic flux and the current are canonically conjugate variables. So therefore quantization is straightforward. So this coordinate we take now write it as an operator and momentum as a operator here, and then we can invoke this quantization rule, and thereby we can quantize the the transmission line, discrete transmission line model there. But as I said at the end of the class, that this Hamiltonian is not still in useful form. We can write it in a more useful form using the normal coordinates, and that's what now we are going to discuss. Because of translational invariance, we can immediately guess that normal modes would be some kind of plane waves, say e to the power I kx, where k is the wave vector and x is the position on the transmission line. So normal modes can be assumed to be or taken to be plane waves, and we want that this k wave vector, k is the wave vector, and this wave vector we want it to be discretized. It is just like the same strategy we have applied when we have quantized electromagnetic wave, if you can remember from first module, where because of boundary conditions this wave vector k got discretized. Here also we are going to adopt the same strategy, and to make k discretized we are going to adopt periodic boundary conditions, and in this regard translational invariance of the transmission line is going to help, because in the transmission line, whether we go towards right or towards left, it doesn't matter, because it is a infinite transmission line and every branch in the transmission line is equivalent. Okay, so because of all these things, mainly because of the translational invariance, we can take our transmission line or imagine our transmission line to be some kind of a ring here, say ring of circumference w, and this transmission line has to be of course now divided into some unit cell size is cell having a length a. Okay, so let us divide it into a number of unit cell size a, and we want that this transmission line has to support a plane wave, and it has to satisfy this condition, periodic boundary conditions it has to satisfy at any point x, say any point x which is equal to x is equal to n into a. It has to be equal to e to the power I k x plus w. So let us say you have, this is your point x, then if you come back to this point, you go in this direction, again come back to this point x, so you should have e to the power I k x is equal to e to the power I k x into x plus w. So this implies that I must have e to the power I k w is equal to 1, which I can write as e to the power 2 pi I into some integer. So immediately you see that our k would be equal to 2 pi by w into some integer. So therefore this wave vector k is now getting discretized. Okay, Now our strategy would be as follows. We have to find an answers for our magnetic flux. We want to decompose into a number of plane waves. Basically, we want to express our magnetic flux as a sum of plane waves, superposition of plane waves, say e to the power I kx, and we are going to put these answers. We are now going to guess the answers. We are going to put these answers in this Hamiltonian. Okay, that's what we are going to do, and then we are going to demand, does these Hamiltonians look like a simple harmonic oscillator Hamiltonian like h cross omega a dagger a plus half, where a is the annihilation operator and a dagger is the creation operator. So this is our strategy. So I have to put here this annihilation operator ak, and because this magnetic flux is Hermitian, so I must have a term like this ak dagger e to the power minus ikx. Now e to the power ikx, this term is dimensionless, this is dimensionless, and creation operator and annihilation operators are dimensionless. So therefore I must have to multiply it by an appropriate constant, say ck, for the kth mode, and I am taking the sum over all the modes k. Okay, and this constant ck has the dimension of magnetic flux, and this constant we are going to determine later. And also, because of translational invariance, whether we go towards right or towards left, it doesn't matter. So we must have to have ck should be equal to c minus k, and for the same reason, because of translational invariance, we must have omega k should be equal to omega minus k. Another important point to note here, that this k lies between minus pi by a to plus pi by a. This could be understood as follows. Say our k is lying between minus pi by a to plus pi by a. Say we take a large k value beyond this range that we are taking. Say k is larger than pi by a, and we evaluate it at some discrete value of x, and we know that x is equal to n integer n into a, so x is scaled as a, and on the other hand this k is inversely proportional to the cell size. So therefore if we take a large k, that is equivalent to considering a plane wave at smaller k, because you see e to the power I kx, because of these relations, so it does not going to make any difference. So therefore we can take k to lie between minus pi by a to plus pi by a. So now we have these answers for this magnetic flux or the coordinate, and we have to put it in this Hamiltonian, but we need to know the answers for this momentum, and that is easy to get because we know that this momentum Pn is related, we have actually worked it out earlier, that this is related to the magnetic flux because by these expressions. So Pn is equal to, let me write here, so Pn is equal to C into phi n, where phi n dot. Okay, so this is what we have, and phi n is this. Okay, now there may be a confusion because I have taken C as my capacitance, so let me take this constant difference. So let's say this is A, not C, so this would be A. Okay, now I have to take the time derivative of this magnetic flux, Now you see the presence of this annihilation operator and the creation operator here, and you know from module 1 that this annihilation operator, it actually varies with time. Its free evolution gives like this, e to the power I omega k t. So we can exploit this, and if we exploit this, then this momentum operator, we can write it like this. So let us, if we just take the time derivative, then we'll get it c into ak, that's the constant now we are taking, e minus I omega k, this is sum over all k, and we have ak operator e to the power ikx minus ak dagger e to the power minus ikx. So we have both now this momentum operator as well as this coordinate phi at our disposal. Now we need to insert the coordinate phi n and the momentum pn into this Hamiltonian. Now this involves a little bit of straightforward but tedious calculations, so I am going to avoid giving you the details of the calculations, but we can work out the details in a problem solving session later. Now here are the key points of the derivations. If you see this Hamiltonian here, we have to take Pn square. Now while taking Pn square, we are going to encounter two sums over k, say Pn square. If I take it, then I will have sum over k and then another sum over k dash, and we'll get terms like c square ak dash minus omega k dash, and then we'll have term ak dash e to the power I k plus k dash x, and then Hermitian conjugate. Okay, so therefore in the Hamiltonian we will have three sums. One would be sum over n, another would be sum over k, and then sum over k dash. However, things get simplified because of an orthogonality condition. Let me write that first, then I will explain. Because of this orthogonality condition, say sum over n e to the power I k plus k dash x would be equal to delta k minus k dash w by a. W is the circumference of the ring when we have taken the transmission line imagined as a ring, and a is the cell size. Let me explain this orthogonality condition. So say if we take k is equal to minus k dash, then you will see that e to the power I k plus k dash x is equal to 1. So therefore we will have this sum over n, and then this would be simply total number of cells in the transmission line, and that would be equal to length of the transmission line divided by the cell size. On the other hand, if k is not equal to minus k dash, then this sum over n e to the power I k plus k dash x would be equal to 0. In fact, you can quickly understand it by going over to the continuum limit. If I go to the continuum domain, then this summation sign would be replaced by an integral. Then this would be dx 1 by a integral dx e to the power I k plus k dash x. Now you know this is nothing but the Dirac delta function, so you have 2 pi by a delta k plus k dash, and you know that when k is not equal to minus k dash, this term would be equal to 0. So that's how all this information that just I discussed is contained in this orthogonality condition. So due to this orthogonality condition, we'll end up in a Hamiltonian where we have a single sum over k, and there would be there will be terms in the Hamiltonian. So one of the terms in the Hamiltonians would be like this, say ak dash w by ak square minus c by 2 omega k square plus 2 by L sine square Ka by 2. Now clearly a term like this containing a bilinear combination of annihilation operator is not wanted, as we expect that our Hamiltonian is going to have this kind of a form that would be AK dagger AK kind of form we are expecting in the after doing all the calculations. So therefore a term like this is we have to actually avoid, and we can actually get rid of this kind of a term if I make this term here to be equal to 0, who is actually imply choosing our frequency omega k as this. You can immediately make it out from this expression here that if I choose omega k square is equal to 4 by LC sine square Ka by 2, then we'll be able to get rid of this term containing bilinear combination of this annihilation operators. And because omega k is positive, so omega k I can write it as this magnitude would be 2 by square root of LC mod sine Ka by 2. In fact, this is the dispersion relation for plane wave propagating on a transmission line. So this is the dispersion relation for a plane wave propagating on the transmission line. Okay, let us plot the so-called WK diagram based on this relation for the transmission line. Let me take my k along the x-axis and frequency along the y-axis. K is lying between say minus pi by a to plus pi by a. As I discussed earlier, all other k's are equivalent. Now near k is equal to 0, I can write sine Ka by 2 to be equal to simply Ka by 2. Then I have omega k is equal to 2 by square root of LC Ka by 2, or Ka by square root of LC. So clearly omega is linear in k, so therefore near k is equal to 0, this omega k curve would be linear. We will have a linear curve here. And again, if you look at Ka is equal to pi, then you will have omega k would be equal to 2 by square root of LC. From this expression, Ka by 2 would be pi by 2, so that would be 1. So you will have here, say you have this height here would be 2 by square root of LC. Similar is the case here at this other end here. You will have this height would be 2 by square root of LC. So I can expect so it will deviate from this linear line and it will go like this, and similarly here it would be, you will have this would be linear near k is equal to 0, but as we deviate from k is equal to 0, it will have a plot like this. It will deviate from the straight line. Okay, so omega k would be, the height would be this much. Alright, so clearly in the linear region, as you can see, omega k is equal to ka by square root of LC, which I can actually write it as 1 by square root of small l small c into k, right? And if you remember, this expression is nothing but the velocity of the wave, and omega k in the continuum limit, actually this is what we got, that the earlier analysis shows that the wave travels with a constant speed v, because small l and small c, the small l is the inductance per unit length of the transmission line and small c is the capacitance per unit length. So, and they are independent of size of the unit cell. So in fact, when we are near k is equal to 0, or that means when we are actually near very small wave number k or large wavelength, as expected we are in the continuous limit. Okay, so as a tends to 0, as the cell size tends to 0, pi by a, as a tends to 0, pi by a moves out. As you can see, this will move out, and similarly this side, and will follow linear dispersion curve. This linear curve will actually go on extending as the cell size tends to 0. Okay, now let us look at the other terms of the Hamiltonian. Now we'll have another term in the Hamiltonian that would look like this. That would be sum over k 2w by ak square, and we have this term c by 2 omega k square plus 2 by l sine square ka by 2, and this would be multiplied by ak dagger ak plus half. And this is the kind of term we wanted, because we have, you see, we have even this 0 point fluctuation term is also there, and this is the desired term because of the presence of this ak dagger ak. And using that relation that dispersion relation that we obtained, this relation that we have, because of this relation, in fact this relation, okay, I can, let me write it here, because of this relation c by 2 omega k square plus 2 by l sine square ka by 2 is equal to 0. I can replace this sine square ka by 2, or this implies I can write that 2 by l sine square ka by 2 is equal to c by 2 omega k square. So if I put this expression here, then I will get my Hamiltonian as sum over k 2w by a small a ak square capital C omega k square ak dagger ak plus half. And I can write it as a more simpler form 2w. You see this capital C, that is the capacitance, and this is A, so I can write it as small c, capacitance per unit length, AK square omega k square AK dagger AK plus half. So we are almost there. Now let us choose h cross omega k. Let us take it such that means this is going to give us a choice for AK. Let me put it as 2wc AK square omega k square, which means that I am taking my AK to be equal to h cross divided by twice CW omega k under root. So if I take my this parameter AK like this, or it is simply h cross divided by twice capital C. CW is C full here, is the capacitance of the full transmission line, and I have omega k, that's the frequency. So this should actually remind you of h cross by twice m omega term when we discuss quantization of mechanical harmonic oscillator. So finally, therefore, we obtain choosing my AK to be like this. So I get my Hamiltonian as sum over h cross omega k AK dagger AK plus half. Alright, so clearly when quantized, our transmission line also look like a collection of independent harmonic oscillators. So this concludes our discussion on quantization of transmission line. Now let us write down the expression for voltage, as it is a physical quantity and our Cooper pair box or artificial atom is coupled via voltage. Please recall that the rate of change of magnetic flux phi, the rate of change of magnetic flux gives us the voltage. This we discussed earlier, and we have our magnetic flux as this is the expression. Now we get h cross, that is our constant A. This constant we have to put there. Then we'll have h cross by twice C, the full capacitance omega k square root, and then we have AK e to the power ikx plus AK dagger e to the power minus ikx. So this is the magnetic flux. So the voltage would be just the time derivative of this magnetic flux expression, and that would be simply minus I omega k h cross by twice C full omega k square root, and here I have AK e to the power e to the power plus ikx plus AK dagger e to the power minus ikx. In fact, there would be a minus sign here, and we have actually exploited the fact that the annihilation operator, its time evolution is given by AK0 e to the power minus I omega kt. Okay, now while we have done the quantization using discrete model, it is perfectly valid for the continuum model also, because only thing is that in the continuum model, so in the continuum model, our cutoff frequency, cutoff wave number will actually go to infinity as a tends to 0. Okay, by the way, you know that the k cutoff for the discrete case, discrete model is simply pi by a, plus minus pi by a. I'm just giving you the only the this one. So on the other side it is minus pi by a. So as a tends to 0, you can see that the cutoff frequency will tend to infinity, and we will have omega in the continuum model. We will have omega is equal to k into v. Okay, so now let us do the quantization of the transmission line resonator. And this is important because we want our artificial atom to interact with the microwave very strongly. Hence, we put our artificial atom inside a resonator. So how we can get a resonator? We can get a resonator by just taking a transmission line and then cut the transmission line at 2 points. So you just take this transmission line, and if we cut it at 2 points, then we are going to get a resonator. Now clearly we cannot use periodic boundary conditions now, as we can no longer assume the resonator to form a kind of ring, as we could do that in the case of infinite transmission lines. So we are now going to discuss transmission line resonator. In fact, quantization of transmission line resonator. So for that, first of all, we need appropriate boundary conditions. As you see, that we cannot use the periodic boundary conditions, but we can still get boundary conditions very easily, because of the fact that suppose we have a transmission line of length d, and its endpoints are is located at say x is equal to minus d by 2, and another end is at x is equal to plus d by 2, and at the endpoints quite clearly the current has to be 0 at this end, and the current at x is equal to d by 2 has to be equal to 0. So we get the boundary condition like this, that current at x is equal to minus d by 2 is equal to 0, and current at x is equal to plus d by 2 has to be 0. This means that because of the relation that we discussed earlier, that the difference in the magnetic flux at two node points in the transmission line is simply given as, we can get the current from this expression. And now in the continuum limit, if we go to the continuum limit, in the continuum limit, we can write this expression as del phi del x, and that has to be equal to 0 at x is equal to plus minus d by 2. So this is going to serve as an important condition, and it will be of very useful while we are going to quantizing the transmission line resonator. Now the next thing is, what about the normal modes? What about the normal modes? Okay, first of all, let us discuss what kind of shape of normal modes we can have. In the infinite transmission line, we had plane waves. However, here we have standing waves, and these standing waves are maybe sine or cosine function. So let us examine first few of the normal modes. So let me say few normal modes. Let us now discuss. Let us say we have a sine function. Suppose here the current at these ends are not I'm going to now I'm going to sorry, not current, we are going to talk about normal modes. So suppose the normal mode has a shape like this. Okay, so this is what I have. That means normal mode means the magnetic flux. We are going to express it in terms of normal modes. So suppose we have a shape like this. Now quite clearly this has a shape of a sine function, and we want at say x is equal to d by 2, I want my sine function to have this form, say sine pi by 2. Okay, so therefore how I can write the shape of this function? So at x is equal to d by 2, I want it to be pi by 2, so my mode function would have this form, sine pi by d by x. Similarly, let me estimate another one. Let us say my normal mode now has this kind of a shape, say, so it's a cosine with here at this end x is equal to minus d by 2 and x is equal to plus d by 2. So this is negative minus 1, say. So therefore again at x is equal to d by 2, I want it to have this form, say cos pi. So therefore my shape of the function, I can write it like this, say x at x is equal to d by 2, I want it to be pi, so my mode function would look like this, 2 pi by dx. Okay, let us do another one. Say this time we have a mode of this type. Say we have this kind of a mode shape, and here it is going to be of this form. At sine it would be x d by, at x is equal to d by 2, I now want it to have 3 pi by 2 value, so the mode function will look like this, sine 3 pi by dx. So this way we can go on writing shape of many modes, but in general the shape of the modes are represented by these functions. So I have say sine n pi by dx for n is equal to 1, 3, 5 and so on, and I have cosine of n pi by dx, and that would be for n is equal to 2, 4, 6 and so on. Okay, so these is our modes. That means the shape of the mode function would look like this. So clearly these modes are orthogonal because these are sine and cosine functions, and we have this orthogonality condition. So orthogonality condition that we are going to use is this orthogonality condition, that would be limit from minus d by 2 to plus d by 2, and I have one function, and then I have phi n dash x dx, that would be equal to d by 2 delta n dash. So these are, it's very easy to understand, and I hope all of you are getting it. Now let us make our answers. Let us assume our flux, magnetic flux, or the coordinate to be of this type. Phi n of x is equal to, it is now sum over all the modes, so sum over this mode, this is our mode function. Just remember I'm using the same kind of a symbol here, but I'm not putting a cap here. Okay, so this is the mode function, shape of the mode function as I discussed here. So this is what I have here, and this I'm going to express in terms of normal coordinates of a harmonic oscillator. So normal coordinates of a harmonic oscillator, I can write it as an plus an dagger. These are the annihilation and creation operators of the harmonic oscillator. And then because this is dimensionless, it has to be multiplied by a constant which we are going to determine later on. So exactly the same procedure that we adopted for the case of the transmission line, the same procedure. Now only thing is that the mode function, the magnetic flux, the answers is now, rather than plane wave, now we are having a standing wave and with different boundary conditions. Okay, then next quantity we require is the momentum. So for the discrete case, you know that the momentum Pn is equal to this capacitance into phi n dot. But in the continuum limit, we are going to use the continuum limit case now. In the continuum limit from classical physics, we know that the momentum, we can write it as c into small c into phi dot x. Small c is the capacitance per unit length, and then this would be, I will write it as an phi n x minus I omega n an minus an dagger. Okay, now taking the idea from classical Hamiltonian for the continuum case. So this is the, in the continuum case, the classical Hamiltonian would be like this: momentum into the coordinate, then minus the Lagrangian. Okay, so this is what we have. So therefore we can write down the Hamiltonian, quantum Hamiltonian, like this. It would be minus integration from minus d by 2 to plus d by 2, and this, now this momentum would be replaced by an operator. So in fact you are going to get it pi square by 2, this is small c, okay, capacitance per unit length, plus 1 by, this is very straightforward and easy to understand. With so much of training already, I think you are easily going to get it. And this small l is the inductance per unit length, and this would be delta x phi of x whole square and dx. Okay, so again I'm going to avoid the detailed calculations. Maybe we will do the detailed calculations in a tutorial problem or a problem solving session later on. Then I will give more detailed calculations there. Now using the answers and the boundary conditions, a similar calculation procedure we can have as we did in the case of the infinite transmission line. And then if we do that, finally our Hamiltonian is going to take this simple form of the simple harmonic oscillator Hamiltonian, h cross omega n an dagger an plus half. Okay, so this is what finally, even in the case of the transmission line resonator, we are going to see that it is also it's a collection of independent harmonic oscillators. Now while we get this, in this case our this constant an, we take it as, we have to choose it like this. It is h cross small c, that is capacitance per unit length, into the length of the resonator into the frequency, and we can write it as h cross divided by the full, now this is the capacitance of the resonator, the full capacitance of the resonator into omega n. So c, this full capacitance is nothing but small c into d. Okay, so, and the dispersion relation we actually got in the process is a simple one, that would be omega n is equal to knv, which I can write it as v into n, kn is pi by d. Okay, this is what I have, and where this v is the velocity of the wave, and that is nothing but square root of small n into small c. And typically for the transmission line resonator is, say it is on the order of 1 centimeter or so, then the frequency would turn out to be in the range of gigahertz. The fluctuating voltage we can obtain as follows. The fluctuating voltage in this case would turn out to be, you just have to take the time derivative of the flux expression, and you are going to get I omega n a n phi n of x a n dagger minus a n. Now, many times rather than writing this expression I into a n minus a n, because you see this is actually related to the momentum, and you know the in Hamiltonian formalism momentum and coordinate are have equal weightage, and therefore we can easily make transformation. So rather than writing it in this form, we can make a transformation or choose our annihilation operator such that we can write this expression as simply a n plus a n dagger, and this is what we are going to use later in this course. And therefore the fluctuating voltage is going to be written like omega n a n phi n of x a n plus a n dagger. The reason I am giving so much stress on this fluctuating voltage is due to the fact that we are going to couple our Cooper pair box with the voltage. When we are going to put it inside a resonator, the artificial atom, that atom is going to get coupled to the voltage V of x. Let me stop here for today. In this lecture, we learned how to quantize an infinite transmission line, and also we learned how to quantize a transmission line resonator. In the next class, we will see how to couple a two-level system or an artificial atom into a transmission line resonator. In the process, we are going to learn about the famous James Cummings model. So, see you in the next class. Thank you.